Okay, so I'm kind of just doing one video for both 9.4 and 9.5. 9.4 is mainly just doing a little bit of vocabulary. It has you calculate some Wronskians again. It's not something I would worry too much about on 9.4. The main takeaway I want you to get from 9.4 is this idea of writing something in a normal form. And that's the idea, is that if you have your vector, now again, this vector is going to be for us just two variables, where x of t and y of t are the unknown functions. And the normal form is going to be when you have the derivative of this vector is equal to a times the original vector for some 2 by 2 matrix A. So again, we're only dealing with the 2 by 2 case in this class. We're only dealing with the case where A is constant coefficients. We're only doing the case where it's homogeneous. So non-homogeneous would be when you had something like a plus B over here. But we're not doing that here. We're just doing x prime equals AX. That's all we're going to be handling here. And so at this point in time, I'm going to go ahead and show you the process by which we can solve one of these. And so here's going to be our example. We're going to solve the equation x prime equals 2, -3, 1, -2 times x. So this is our coefficient matrix A here. And I've mentioned it in the Zoom meetings, but we'll just show you right here. We're going to need to find the eigenvalues and eigenvectors for this. And so, okay, so to find my eigenvalues, we have to do determinant of A minus lambda I, like we did in the past. So determinant of 2 minus lambda minus 3, 1, minus 2 minus lambda. And let's see here, we're going to have lambda squared plus 2 minus 2 is 0, and then it's going to be minus 4 plus 3 is minus 1. And so we're going to get two values of lambda here, positive 1 and negative 1. So we're going to go ahead and look at lambda equal to 1, and we're going to try to find an eigenvector for this. So remember how we do that. We do A minus lambda I x equal to 0. And so we write our equations here, subtracting 1 from it. I'd have 1 minus 3, 1 minus 3, 0, 0. And if you do your reduced row echelon form here, you get 1 minus 3, 0, 0, 0, 0. So that means x minus 3y is 0, x is 3y. And so your eigenvector is going to be 3, 1. And then we're going to go ahead and do our lambda equal to -1 here. And we do our same idea here, but this time we're subtracting a -1, which is the same as adding a +1. And we get, let's see here, 3, -3, 0, 1, -1, 0. Reduced row echelon form. We get x minus y is 0, x equal to y. And we get a nice eigenvector of 1, 1. And then, turns out, here's how you solve the differential equation. Now, there's just going to be one more step here, is we write down that the x vector that we're looking for is some constant times e to the first eigenvalue times the first eigenvector plus c2 times e to the second eigenvalue times the second eigenvector. And this right here is a perfectly good answer. Or if you'd like writing it in maybe a slightly nicer way here, you can write out x then is going to be 3c1 e to the t plus c2 e to the negative t and c1 e to the t plus c2 e to the negative t. Or also equivalently, we could say x of t is 3c1 e to the t plus c2 e to the negative t, and y of t is c1 e to the t plus c2 e to the negative t. And so any of these three ways is a perfectly valid answer to the problem. And that's it. So once you find your eigenvalues and eigenvectors, you're done with the problem. You already have the answer just written out right there. So this is the process here. I'll do another video with another example. The next one's going to have a initial condition to deal with. But this is the main focus of what you want to have for the rest of the semester.